new concept and knowledge in modern physics. The main focus of our discussion is all about problem solving and photoelectric effect. The problem that we are going to be solving is this, which says that aluminum has a work function of 4.08 electron volts. Find the minimum frequency and the wavelength of light that can cause photoelectric effect in aluminum. But before I teach you how to solve this problem, you must know first that
photoelectric effect is a way that uses light to eject electron out of a metal surface. The photon of light have energy equal to the product of Planck's constant and frequency, where Planck's constant is equal to 4.14 times 10 raised to negative 15 electron volts, or 6.626 times 10 raised to negative 34 joules per second. And because frequency is equal to the speed of light over lambda, we can also get photons energy using this equation, where speed of light is equal to 3 times 10 raised to 8 meter per second. If that photon hit an electron, all of its energy will be given to the electron. And if the photon's energy is high enough, electron will surely be ejected from the metal with a specific kinetic energy. The minimum energy needed to release the electron from a metal is called the work function of the metal, represented by this sign, and is equal to the product of Planck's constant and threshold frequency of the metal. The maximum kinetic energy of ejected electron or photoelectron is equals to 1/2 times mass of photoelectron times maximum speed, or simply energy of photon minus the work function.
So now that you already know the formulas and the concept in photoelectric effect, we can start solving the problem. Given only is the work function, which is 4.08 electron volts. First, we must find the minimum frequency. To get the frequency formula, we will derive the work function formula, which is equal to the product of the Planck's constant and then the frequency. Divide both sides with Planck's constant, cancel it, and then the frequency is equal to the work function over the Planck's constant. Then we are going to substitute it. Work function is 4.08 electron volts divided by the Planck's constant, which is 4.14 times 10 raised to negative 15 electron volts. When you divide it, we will get 9.86 times 10 raised to negative 16. Unit of measurement will be hertz, or 1 cycle per second. Next, we will solve for the value of the wavelength, or lambda. The corresponding wavelength of a light beam can be get using the formula of the speed of light, which is equal to the product of frequency and lambda. We will derive it, divide both sides with the frequency, and cancel. So now we already get the formula of the wavelength, which is equal to the speed of light divided by the frequency. Then we will going to substitute for the value of the speed of light, which is 3 times 10 raised to 8 meter per second divided by the frequency 9.86 times 10 raised to negative 16 cycle per second. When you divide it, we will get 3.043 times 10 raised to negative 9. And then we will cancel this out, and the unit of measurement will be in meter. Usually, wavelength is in the form of nanometer. So we will have to convert it into nanometer. But for easier conversion, we will move this decimal point 2 places going to the left, and this will become 304.3 times 10 raised to negative 7 meter. And in conversion, we must know that 1 meter is equals to 1 times 10 raised to 9 nanometer. So we will convert 304.3 times 10 raised to negative 7 meter into nanometer. 1 times 10 raised to 9 nanometer over 1 meter. Cancel the meter sign. And when you multiply it, we will get 304.3 nanometer. So our wavelength is equals to 304.3 nanometer. There you have it. We already get the minimum frequency and the wavelength of light that can cause a